Let us continue nitrogen family. In the nitrogen family, we will continue from chemical properties of corn nitric acid. Now we will take metals iron, chromium, aluminum. Iron, chromium, aluminum with corn nitric acid. With corn nitric acid becomes what in the sense passive. Becomes passive. What does it mean? Iron, chromium, aluminum with corn nitric acid, no reaction, becomes passive. What does it mean? That we'll see. Now we will take this is the aluminum plate. This is the aluminum plate. In this aluminum plate, it is a surface aluminum, it is bulk aluminum, it is surface aluminum. This corn nitric acid is giving nascent oxygen because it is oxidizing agent. It is converting the surface aluminum into Al2O3. So the surface aluminum becomes what in the sense Al2O3 we are seeing. Surface aluminum becomes Al2O3 like this. Surface aluminum becomes Al2O3. This Al2O3 is insoluble. Therefore, it is not allowing corn nitric acid to go into the bulk. So bulk aluminum is unable to get nascent oxygen. Therefore, bulk aluminum is not going for chemical reaction with the concentrated nitric acid. Therefore, we can say aluminum is passive in corn nitric acid. Similarly, iron and chromium. So we can say iron, chromium and aluminum are passive in corn nitric acid. Like that we can say. Next, we'll see noble metals. How noble metals involve in a concentrated nitric acid means no reaction, but noble metals will dissolve in aqua regia. So what is aqua regia? That we'll see. Aqua regia is a corn HCl plus corn nitric acid, we can say as aqua regia. So aqua regia is what in the sense? Corn nitric acid plus corn HCl. Corn nitric acid plus corn HCl is nitric, the aqua regia ratio is 1:3. Concentrated HCl 3 parts we have take, corn nitric acid 1 part we have take. Now noble metals dissolve in this aqua regia. Sir, how the noble metal gold is involving in chemical reaction, that we will see. First, this aqua regia HNO3 reacting with HCl to give nitrosyl chloride and nascent chlorine. Now we will balance this one. For balancing, we will balance this one like this. Okay, nascent chlorine is available. This nascent chlorine is taken by gold. Gold takes this nascent chlorine and becomes AuCl3, auric chloride. This auric chloride dissolves in HCl and forms complex. Complex is auric HAuCl4. HAuCl4. Like this, complex is produced. Due to formation of this complex, this gold dissolves in aqua regia, we are seeing. So this aqua regia gives nascent chlorine. Gold undergoes oxidation and becomes auric. Auric with HCl gives complex HAuCl4. Sorry. Noble metals with aqua regia reaction we have seen. Next we will see about a brown ring test. Brown ring test we will see. In the brown ring test, we can say we are using a concentrated nitric acid we are using for brown ring test. Next we will go for uses of nitric acid. This nitric acid is used for manufacturing fertilizers, ammonium nitrate. Then it is used for preparing explosives. Then it is used for preparing nitroglycerin, trinitrotoluene. Then used for etching metals, etching of metals. Etching of metals in the sense, over the metal, we can write, if we want to write anything, we can use corn nitric acid. Just like how we are writing something on over the paper using pen like this. Instead of ink, corn nitric acid we have to use for writing letters over the metals. Okay, then this corn nitric acid is used as oxidizer in rocket fuels. Okay, next we will go for allotropes of phosphorus. Allotropes of phosphorus, one is white phosphorus, we can say. For this, another name is what in the sense? Yellow phosphorus. White phosphorus, another name is yellow phosphorus. Next, red phosphorus will take. Allotropes of phosphorus, in that white phosphorus, and another one is red phosphorus we have taken. This white phosphorus odor is garlic odor. White phosphorus is garlic odor. Red phosphorus odorless. Smell is not there. Odor is not there. This white phosphorus is poisonous, but red phosphorus is non-poisonous, not poisonous. This white phosphorus insoluble in water. Red phosphorus also insoluble in water. White phosphorus, it is soluble in carbon disulfide, CS2. Red phosphorus insoluble in carbon disulfide. This white phosphorus is soluble in carbon disulfide. Red phosphorus is insoluble in carbon disulfide. Then this shows chemiluminescence. It shows chemiluminescence. Chemiluminescence. It is not showing chemiluminescence. It is not showing chemiluminescence. What is chemiluminescence? That means white phosphorus burns with atmospheric air under room temperature itself and gives phosphorus pentoxide. White phosphorus burns with oxygen under room temperature and gives P4O10. Burning in the sense it is giving light. Therefore, it is glowing. It glows. This process is called chemiluminescence. It is chemical reaction. Therefore, chemiluminescence in the sense it is emitting light. It is emitting light. Therefore, chemiluminescence we can say. Therefore, white phosphorus burns with atmospheric air under room temperature, but red phosphorus is not burning, is not showing chemiluminescence. That's why if you see bones, if you see even in dark room also bone will be appearing. If there is no light, though there is no light, bone will be visible in the dark room. Bone will be visible in the dark room. Why? Because bone contains white phosphorus. That white phosphorus undergoes chemiluminescence. That is burning with atmospheric air under room temperature. Due to burning, it is emitting light. Okay, sir. Next, this white phosphorus reacts with a sodium hydroxide solution on boiling. White phosphorus reacts with sodium hydroxide solution on boiling. Sorry, what does it give? White phosphorus with the sodium hydroxide on boiling gives what in the sense? Phosphine and sodium hypophosphite. Sodium hypophosphite. Okay, so white phosphorus on boiling with the sodium hydroxide solution gives phosphine and sodium hypophosphite. White phosphorus on boiling with the sodium hydroxide solution gives phosphine, we are saying, whereas red phosphorus is not going for this reaction. Red phosphorus is not going for reaction with the sodium hydroxide solution. So, next, this white phosphorus is more reactive. Red phosphorus is less reactive. Why is it so? That we'll see. White phosphorus is more reactive, whereas red phosphorus is less reactive. What is the reason? We'll see. We'll see the structure of white phosphorus. We'll see white phosphorus structure in which white phosphorus structure is tetrahedral. In the tetrahedron corners, phosphorus atoms will be there. In the tetrahedron corners, phosphorus atoms will be there. Between phosphorus atoms, single bond will be there. Single bond will be there like this. So this is a white phosphorus P4. Here tetrahedron is the shape of this. In the tetrahedral corners, phosphorus atoms present. At the center of tetrahedron, no atom is present. Here, what is the angle? What is the angle? The angle is 60 degree here. Angle is 60 degree. Angle is 60 degree. Bond angle is very less. That means tetrahedral means normal angle is 109 degree 28 minutes. But it is less than 109 degree 28 minutes. Therefore, here Bayer's strain is there. Angle strain is there. Because of strain, it is having low stability, therefore more reactive. So what about red phosphorus? That we'll see. In red phosphorus, how it is there, we'll see. In red phosphorus also, tetrahedron will be there like this. We will write tetrahedron. Now what happens means this bond comes in between these two. This bond goes here. Therefore, bond comes like this. Here continuation, here continuation. It is red phosphorus. Red phosphorus is polymeric. Therefore, red phosphorus is polymeric. Therefore, it is less reactive, more stable. White phosphorus is more reactive and less stable. Okay. So, reactivity of white phosphorus and red phosphorus we said. Then, how to prepare red phosphorus? That we will see. How to prepare red phosphorus? That point we will see. Red phosphorus is prepared from white phosphorus. We are taking white phosphorus at 573 Kelvin. Then inert atmosphere we are providing. Inert atmosphere for several days the white phosphorus is left at 573 Kelvin. Then it is converting into what in the sense red phosphorus. It is converting into red phosphorus we are seeing. Okay. Red phosphorus we are using in matchstick. Why we are using red phosphorus in matchstick? In the sense it is non-poisonous. Another one is its ignition temperature is not room temperature, it is high temperature 533 Kelvin. Its ignition temperature is not room temperature, that is high temperature, that is 533 Kelvin. Therefore, we are using red phosphorus in the matchstick. In the matches we are using. But white phosphorus we are not using. Why? Because its ignition temperature is room temperature. At room temperature itself, it will start burning without igniting, and it shows and it is more reactive. It is poisonous. Therefore, only we are not using white phosphorus in the matchsticks. Next, phosphorus we will see. Next, allotrope of phosphorus, alpha black. Alpha black phosphorus we will take. This alpha black phosphorus, how to get in the sense? We are taking red phosphorus. This red phosphorus is heated to 803 Kelvin. 8 phosphorus is heated to 803 Kelvin. We are getting a alpha black phosphorus. This alpha black phosphorus is not burning in air. Next we will take beta black phosphorus. Beta black phosphorus. How to get beta black phosphorus means we are taking white phosphorus. White phosphorus we are taking. It is heated to 473 Kelvin. 473 Kelvin under pressure. We are getting beta black phosphorus. It is not burning with atmospheric air up to 673 Kelvin. It is not burning with atmospheric air up to 673 Kelvin. Next compound, phosphine. We will take phosphine. How to prepare phosphine? That we will see. We will take calcium phosphide. Calcium phosphide is Ca3P2. Phosphorus oxidation number is -3 here. Calcium phosphide is treated with water. Phosphorus, this phosphide P3 minus undergoing hydrolysis. This P3 minus we can write here. Calcium we can write here. Cross multiply you will get calcium is +2, phosphorus is 3 minus. This phosphide takes H plus from water and becomes phosphine. Calcium takes OH minus from water and becomes calcium hydroxide. So calcium phosphide undergoes hydrolysis with water to give what in the sense phosphine. Then calcium phosphide with HCl. Calcium phosphide with HCl gives a phosphine PH3. Phosphide P3 minus takes H plus and becomes phosphine. Then we will get calcium chloride. So calcium phosphide reacts with the dilute HCl to give what in the sense phosphine, we can say. With the dilute HCl, it gives phosphine. So next we will see laboratory preparation of phosphine. Next we are going for laboratory preparation of phosphine. Now we will take white phosphorus. To this we will add sodium hydroxide solution. Sodium hydroxide solution, and it is heated. What we are getting in the sense we are getting phosphine, then sodium hypophosphite will get. Sodium hypophosphite will get. Now we can do, instead of sodium hydroxide, we can use even calcium hydroxide. If we use calcium hydroxide instead of sodium hydroxide, we will get calcium hypophosphate. We will get calcium hypophosphate, we will get it. Sir, in this method, we are using inert atmosphere. What is the inert atmosphere we are using in the sense? Carbon dioxide gas, otherwise hydrogen gas. This inert atmosphere we are using. Why to use this inert atmosphere? For what sake we have to use this inert atmosphere? Because phosphine burns in air. Phosphine burns in atmospheric air. In order to avoid that, we are using inert atmosphere, carbon dioxide or hydrogen we are giving. Set. Then the phosphine obtained here contains impurities. What are the impurities in the sense? One is white phosphorus. Next one is diphosphine. Diphosphine. These impurities present in the phosphine obtained here. These impurities, due to impurities, what will happen? Due to impurities, this phosphine becomes flammable. Why? Because impurities catches fire easily. Since these are burning, it is providing ignition temperature to phosphine, therefore phosphine becomes flammable. Otherwise, phosphine is non-flammable. Pure phosphine is non-flammable. Impure phosphine is flammable because of impurities like this. These impurities catches fire easily and burning. Because of them, it is getting its ignition temperature, therefore it starts burning, therefore it becomes flammable. Phosphine becomes flammable. Therefore, whenever we want to use phosphine, use pure form of phosphine, not impure form of phosphine. How to check whether phosphine is pure or impure? How to check? That we will see. Now, impure phosphine we will take. That impure phosphine we will pass into HI solution. HI solution. Impure phosphine we are passing into which solution means HI solution. What will happen now? That we will see. So, phosphine will react with HI and becomes phosphonium iodide. Phosphonium iodide, which is a salt which goes to water. Remaining impurities. Here, what we have to do in the sense, we should not treat with the aqueous solution. Water should not be there. So, this impure phosphine, we have to pass over HI, hydrogen iodide, not solution. We should not take solution. HI, we have to take. That HI gas should be passed over impure phosphine. Phosphine alone react with HI and become phosphonium iodide. These impurities do not react with HI. So the impurities are gas. Phosphonium iodide is solid. That means it is separated from the impurities. Then to this phosphonium iodide, potassium hydroxide is added and it is heated. What happens means phosphonium iodide decomposes to give phosphine vapors. So we can get phosphine vapors. This phosphine vapors is not having any impurities now. Okay. So how to convert impure phosphine into pure phosphine? Take impure phosphine. It is gas. Pass HI gas into this. In the impure phosphine, phosphine alone react with HI to give phosphonium iodide salt, solid. Rest of the impurities are in gaseous state, P4 and P2H4 in gaseous state, which separates from PH4I. Now phosphonium iodide salt is in solid state. To this add potassium hydroxide and heat. It is decomposing to give phosphine gas. So you collect this phosphine gas. What is the remaining means potassium and iodine becomes potassium iodide and water will get. So we have got what in the sense phosphine gas we have got, phosphine vapors we have got. Okay, this phosphine vapors is not containing impurities, therefore it is pure form of phosphine. Okay, sir. Next, what are the properties of phosphine? We'll see. Phosphine is colorless, rotten, fish smell. If fish is getting destroyed, then what smell we'll get? That smell it is giving phosphine. Phosphine is highly poisonous. It is exploding in contact with oxidizing agents like nitric acid, chlorine, bromine. Phosphine is slightly soluble in water. Set. Next properties we'll see. Aqueous solution of phosphine decomposes in the presence of light. So now we will take aqueous solution of phosphine. In the presence of light, it is decomposing to give what in the sense red phosphorus and hydrogen gas. It is giving red phosphorus and hydrogen gas. Phosphine burns with air. Therefore, it is giving what in the sense phosphorus with oxygen gives phosphorus pentoxide. Hydrogen with oxygen gives water. Next, phosphine reacting with the salts. That means copper sulfate salt we will take. Phosphine we will add. What happens means copper with phosphorus gives cupric phosphide Cu3P2. Copper oxidation number is +2, phosphorus oxidation number is -3. Then sulfuric acid will be obtained. So copper sulfate, copper, phosphine, phosphorus becomes cupric phosphide Cu3P2. Next reaction, mercuric chloride with phosphine gives mercuric phosphide Hg3P2 and HCl. Mercuric phosphide Hg3P2 will be obtained. Next, where this phosphine is used in the sense when the ship gets some danger in the sea, then this phosphine will be used by them in order to give signal. In order to give signal, that means we are in danger. In order to give such a type of signal, this phosphine will be used in ships. How they are using that we will see. In them, they have one container. In the container, what will be packed in the sense calcium carbide, that means calcium acetylide, then calcium phosphide is packed in the container. Whenever they want to indicate we are in danger, they will make a hole in the container and they will throw the container into the water. Due to hole, water enters into this. Calcium acetylide undergoes hydrolysis. Calcium acetylide undergoes hydrolysis. Calcium acetylide, we can write calcium ion like this. Acetylide ion, we can write like this. This acetylide ion takes H plus from water and becomes acetylene gas. Acetylene gas, we got it. Acetylene gas, we got it. Calcium phosphide undergoes hydrolysis. In the calcium phosphide, calcium ion is there and the phosphide is there. Phosphide takes H plus from water and becomes phosphine. Phosphine is gas. Along with this, P4 impurity is produced and diphosphine impurity is produced. Phosphine and diphosphine burns in the room temperature itself. Because of this burning, phosphine gets ignition temperature, phosphine starts burning. Because of phosphine burning, acetylene gets enough ignition temperature and it starts burning in a non-luminous flame. Non-luminous flame, that means bright flame, bright luminous flame, that means a lot of smoke will come. Lot of smoke will come when acetylene burns. Okay, so this acetylene is burning with a bright luminous flame. Therefore, it is giving signal to the uh, to others such that we are in danger. For that case, it is used. This signal is called Ohm's signal. We are calling this as a Ohm's signal. We are saying. Sir, okay. Next, we'll see oxides of phosphorus. We'll go for oxides of phosphorus. How to prepare oxides of phosphorus? We'll see. We'll take white phosphorus. To this, we will supply limited amount of oxygen gas. We will get a phosphorus trioxide P4O6. Phosphorus trioxide P4O6. We will take white phosphorus. We will pass excess of oxygen gas. Excess of oxygen gas. It is allowed for burning. We are getting phosphorus pentoxide P4O10. So white phosphorus P4 with limited oxygen, we are getting phosphorus trioxide P4O6 in dimeric form. Excess oxygen means phosphorus pentoxide we will get, that is P4O10. This P4O6 with water, P4O6 with water gives H3PO3, phosphorus acid. P4O10 with water gives H3PO4, phosphoric acid, H3PO4. So oxides of phosphorus means one is P4O6, another one is P4O10. P4O6 with water gives H3PO3. P4O10 with water gives H3PO4. So now we will see P4O6 structure and P4O10 structure. We will see. In P4O6 structure, what we have to do means phosphorus atoms will be in the corners of tetrahedron. In the P4O6, phosphorus atoms will be in the corners of the tetrahedron. Between phosphorus atoms, oxygen atoms will be there. Between phosphorus atoms, oxygen atoms will be there like this. It is called P4O6. Now P4O10. P4O10, if you want, means what you have to do means give the additional 4 oxygens to each phosphorus with a double bond. Here one O, here one oxygen, here one oxygen, here one oxygen. It is called P4O10. If you remove double bond oxygen, double bond O, if you remove, you will get P4O6, you will get. Next, we will go for phosphorus trialides. Phosphorus trialides. In this, X is equal to what in the sense? Halogen, that is chlorine, bromine, iodine. Halogens we can say in the place of X. Now we will see preparation of PCl3. Preparation of PCl3 we will see. Now we will take white phosphorus that is treated with chlorine and ignited. What happens means we are getting PCl3. Take Cl2 limited. Don't take excess. If you take excess, you will get PCl5 and Cl2 should be dry. Otherwise, if water is there, PCl3 undergoes hydrolysis to give H3PO3 set. So we are taking white phosphorus. Dry and limited Cl2 we are passing and heating. What we are getting means PCl3 we are getting. Next, this white phosphorus is treated with thionyl chloride. We are getting PCl3. So white phosphorus is treated with thionyl chloride SOCl2. On heating gives PCl3. Then SO2, S2Cl2 will be obtained. S2Cl2, sulfur monochloride. S2Cl2 we have to call it as sulfur monochloride. So white phosphorus with thionyl chloride on heating is PCl3, SO2 and S2Cl2, thionyl chloride. S2Cl2 is sulfur monochloride. So preparation of PCl3 is so and so. Next we will see properties of PCl3. Properties of PCl3. PCl3 is colorless, oily liquid. It is PCl3 is liquid. How it will be there means like oil. Then PCl3 undergoes hydrolysis to give what in the sense H3PO3, H3PO3 and HCl. Here phosphorus oxidation number is +3. Here also +3. So PCl3 on hydrolysis gives H3PO3. So you see that +3 means P2O3 you take. Otherwise, P4O6 you take. This on hydrolysis gives H3PO3. Okay. Even PCl3, here phosphorus plus 3 oxidation number. This also on hydrolysis gives H3PO3. So PCl3 undergoes hydrolysis to give H3PO3, we can say. Then acetic acid reacts with PCl3 to give what in the sense? In acetic acid, the OH group is replaced by Cl. OH group is replaced by Cl. Therefore, acetyl chloride we are getting. PCl3 becomes H3PO3. In H3PO3, phosphorus oxidation number is +3. Then we will take ethanol, CTH5OH, ethanol we will take. This with the PCl3 gives what we will see. In ethanol, the OH group is replaced by Cl. Therefore, we are getting ethyl chloride. Phosphorus becomes H3PO3. Okay. So, acetic acid becomes acetyl chloride, ethanol becomes ethyl chloride, phosphorus becomes H3PO3, we can say. So, for balancing, we will write here 3. Okay. Next, we will take a phosphorus pentahalide, we will take. Phosphorus pentahalide. In the place of halogen, we can take FClBr. I is not coming. PI5 is not existing. Phosphorus pentaiodide is not existing. Okay. How to prepare PCl5? That we'll see. PCl5 preparation. Take white phosphorus. Take dry Cl2 and excess Cl2 and heat. You will get PCl5. It should be dry and it should be excess. Then only we will get what in the sense PCl5 will get. Then white phosphorus with sulfuryl chloride, SO2Cl2, sulfuryl chloride we are taking. It is what in the sense sulfuryl chloride. Sulfuryl chloride. White phosphorus is heated with the sulfuryl chloride. We are getting PCl5 and SO2. PCl5 and SO2 we are getting. Here, in this reaction, we said Cl2 should be dry and excess. If you take limited, you will get PCl3. If water is there, then it will undergo hydrolysis. Therefore, it should be dry. Cl2 should be dry. So, then properties of PCl5 will see. PCl5 is yellow color, yellowish white powder. PCl5 is yellowish white powder. Then we will see hydrolysis of PCl5. We will see hydrolysis of PCl5. PCl5 undergoes hydrolysis. PCl5 undergoes hydrolysis to give what in the sense POCl3. POCl3 on further hydrolysis gives what in the sense H3PO4. H3PO4. So PCl5 undergoing hydrolysis to give what in the sense POCl3 we can see. How the hydrolysis takes place that we will see. Now we will take PCl5. We are taking PCl5. Now hydrolysis means a reaction with water. In the water, oxygen is having lone pair. Lone pair is attacking this phosphorus. Cl is leaving. Here, this bond is shifting to oxygen. H plus and Cl minus becomes HCl. And Cl is replaced by what in the sense OH. Similarly, another one. Similarly, another Cl. Another Cl also replaced by OH. Like this. Now, what happens means this bond is shifting here, this bond is shifting. Therefore, we are getting what in the sense POCl3. POCl3 on further hydrolysis gives what in the sense H3PO4. H3PO4 we are getting. Okay. So, this POCl3 structure is what in the sense like this. POCl3 structure is like this. It is undergoing further hydrolysis. That means Cl is replaced by OH. So, you are getting H3PO4. H3PO4 structure is like this. H3PO4 structure is like this. So PCl5 on hydrolysis first gives POCl3, then gives H3PO4. So PCl5 on partial hydrolysis gives POCl3. PCl5 on complete hydrolysis gives H3PO4. Next, this PCl5 solid on heating gives PCl5 gas directly. Therefore, PCl5 undergoes sublimation. PCl5 undergoes sublimation PCl5 gas on further heating gives decomposing to give PCl3 gas and Cl2 gas. PCl5 gas on further heating undergoes decomposition to give PCl3 gas and Cl2 gas. Why is it so? Now we will see the PCl5 structure. In PCl5 structure, these three chlorine atoms present in equatorial position. These three chlorine atoms present in equatorial positions. For equatorial position means bond angle is 120 degree. This chlorine present in axial position, axial chlorine. It is also axial chlorine. Here what is the bond angle means 90 degree. So bond angle is high, therefore repulsion is high. Due to high repulsion, axial chlorine goes somewhat far away. Therefore, in PCl5, this axial bond length is high. Axial bond length is high. But equatorial bond, this is equatorial bond. This equatorial bond length is low. Equatorial bond length is low. Equatorial bond length is low. Axial bond length is high. Therefore, PCl5 on heating, this bond breaks easily. PCl5 on heating, the axial bonds break easily. So we are getting Cl2. Remaining is what in the sense PCl3. So PCl5 on thermal decomposition gives what means PCl3 and Cl2 we can say. Let us stop.